Yeah, so for today, we will learn map overlay. So you will learn how to create new geometries by adding, subtracting, intersecting two geometries or more. You will combine geometries based on common attributes, so dissolve them. You learn how to dissolve them. It's very similar to, well, you know what it is in GIS, but it's also very similar to grouping with the grouping that we did with pandas last period and again, first week of this course. And you will learn how to create categories for numerical data based on classifiers. So we will learn how to work with data classification, for example, for making maps. So, for example, you're familiar with natural breaks or quantiles, equal interval, different kinds of classification methods. We see how to apply them in Python. And yeah, and one small part is simplifying geometry. So if, for example, we will work with the data of a river that has very complex shape. And sometimes for cartographic purposes, you may want to simplify the shape of the geometry. And we will see how we can do that using Shapely. So that's the agenda for today. I will go to Noppe. And we start with overlay analysis. So overlay analysis in GIS is a range of operations in which two or more vector data are combined to produce new geometries. Typical overlay operations include union, intersection, difference. So there are a bunch of things. There's more than this. We will see later. But these are the most common ones. So you have two or more geometries, and you want to do an intersection overlay analysis to see what is the common area between those geometries. Sometimes you need to do a union. So it's the combined area of two or more geometries that you might have. And then we have symmetrical difference, which is basically the opposite of the intersection. And you have difference, which is directional. So A minus B or B minus A, you know, the part that is in A but not in B. So that's difference. So these are the things. We will practice with some of these. And there's a function for that in GeoPandas, so it's easy to apply these. Yeah, so the data that we will be working with, it's some data set that probably you have come across in your other courses. It's the travel time matrix that has been developed, or I guess already a decade ago. And it's been updated regularly. It was developed in Tuuli Toivonen's team in Digital Geography Lab. So it's a grid data of the whole Helsinki metropolitan area, so including Espoo and Vantaa. And it basically is a very large data set. If you download the whole thing, it's like 50 gigabytes if you download it in CSV format. And it has all the distance, all the travel time calculations using different travel modes from anywhere to anywhere in Helsinki metropolitan area. So it's a data that has been used quite a lot in research and also in practice, like City of Helsinki, HSL. So it's a very good data set to work with. And we will see a few examples of it during this course as well. Yeah, so we will work with one of the CSV files, one of the, well, this is in GeoPackage format, but one of the files. As I said, there's like thousands of files. And that contains the travel times to Helsinki Central Railway Station. So it's just one GeoPackage that we'll be working with, and we use it a few times today for showcasing, practicing a few of the things that we will cover today. Yeah, we also have another data set which is also in GeoPackage format, and that's just the simple boundary of the Helsinki region. One of the things we will be doing in the first part is to clip our data to Helsinki. As I said, the full data set covers the whole Helsinki metropolitan area, but the first thing we do today is to clip the data to Helsinki, and clipping is also a very useful operation in GIS. So we will see how that works today. So let's get it started. As usual, we run the first cell, which defines the path to our directories using the pathlib library. The code in the second cell is also already typed in. So we are importing GeoPandas and loading our grid data from our data directory and also the boundary of Helsinki municipality. So let's just run this cell. So this is an error that we probably have noticed. It has always happened when I use GeoPandas on Noppe. It doesn't seem to affect our work. So it has some problem fetching the database of the projections, but yeah, it's annoying, but it doesn't affect the operation apparently. Yeah, so now that the data is loaded, let's start by quickly visualizing what we have so we know what we are working with. As I say every week, we are going to revisit the topic of visualization, but we are doing GIS, so it's hard to avoid maps. So I will map the grids. So grid.plot. And I'm going to apply a face color, something neutral to it for now. So I will go with gray. And I want to add the Helsinki boundary to the same map. So Helsinki dot plot. So I will add it to the same axis that we already created. So it will be in the same map. Then you can specify what face color, so what is the infill color. I just want the boundary, so I will just leave it empty. So to leave it blank, you can apply the color none. So it won't add any infill color. You will just have the boundary. And for boundary, you can specify what color you want by setting a value to the edge color. So I will go with blue, but you can choose whatever color you prefer. Okay, so this is a quick map of our data. So this is grid, but you are very zoomed out, so you don't really see the grids, but there are grids, I guess. Is 250 by 250, if I'm not wrong. But yeah, so this is the grid, and this is the Helsinki border. So what we are going to do in the first step is to clip our data, so to get rid of everything we have outside the boundary. So this is the whole travel time matrix from the whole region, and it contains 13,000 grid squares. That covers the whole Helsinki region. Yeah, so as I mentioned during the last 2 weeks, well, when you're working with Python, coordinate systems are particularly important when, like compared to when you're working with software, and it is even more important when you're doing any kind of overlay analysis, because you're essentially comparing the coordinates, and the comparison wouldn't make any sense if the layers are in different coordinate system. So I'm going to print, I want to check what coordinate system I have the Helsinki border data in. So I will go with helsinki.crs. I will print. So it is coming in 3067, which is already good. It's the coordinate system the projected system we often use in Helsinki area. But to make sure that the other layer is also in the same coordinate system, I have written an assertion. So you don't have to type anything, just it's an assertion checking if well, we already know this is 3067, so I'm making sure that this is also in the same. So let's just run this, no errors, so safe to assume that the other layer is also in 3067, which is great. We don't have to do any transformation. Okay, so for doing map overlay, there is a built-in function in geodata it's a method of geodata frame, so it's basically a function coming as part of GeoPandas, and it's called overlay. So with overlay, you just provide what are the layers that you're doing overlaid on and the method. So are you going with intersection? Are you going with union? So yeah, so if you check the documentation of GeoPandas, you can see that there are a bunch of options available to you. So intersection, union, symmetric difference, and identity. Identity is less often used, but do you know what it is? So identity is like, so it keeps the original. So if you have a left layer, you have a right layer, it keeps the geometry, the full geometry of the left layer. But wherever there is overlap with the right layer, it reads the properties, the attributes. So you want to keep your full data, but if there is an overlap, you would read the attributes from the other data. It is less commonly used, like at least I've seen it less, but it's also one option. But now we are going with intersection because we want to clip our data. So this is how we do it. So I will create a new variable, and I will call it intersection. And this is how we apply the overlay. So grid.overlay. So grid is my left layer. And this is the method I'm using that works on geodata frames. Here you specify the right layer that you're using in your overlay. So it was the Helsinki border. And then you have to specify what is the overlay method you're using a parameter called how. So you pass a string, and it can be any of these options up here. We will go with intersection as our overlay method. So let's run this. Okay. So now that we did the clipping or did the overlay analysis, next thing I'm going to do is to create a quick plot of my map, of my clip data. I will also change the color a bit. So I will set the color to blue. So you can go for B as short, or also you can type in blue. Okay, so as you can see, you ended up with a smaller data set only containing the grid cells from Helsinki area. Yeah, so I modified you don't have to do this, but I modified the coloring to show you that this is the kind of grid that we are working with. Okay, so now we already have a visual understanding of what kind of data we are working with, but we haven't yet looked at the attribute table or the attributes of our data. So as usual, let's look at the head of the data. So remember, we stored the new clip data under a variable called intersection. Yeah, so you have many columns in your data set. And yeah, so of course, if you need this data for something else in future, you can check out the documentation to see details of what the columns mean and how they have been calculated. But some of the names you can guess. So it's like car distance. So the distance if you go by car from any point within the area to Helsinki railway station. And there's also time. So it takes 40 minutes from this particular grid. So PT is public transport, again, like distance and time. And there's also like time during different times of the day. So how long does it take with public transport during day or in middle of night? So it's a very rich data set with many columns. So as you can see, due to the overlay analysis, the dataset contains the attributes from both input layers. So you kind of do a special join. So you end up with, when there isn't matching feature on the other side, you end up with the attributes of that one as well. So let's save this output, and we are going to use it later on today. But now I'm saving it as a geo package, and I'm specifying a layer name. And we are going to use this later. So we have been using layers already many times, but we haven't really talked about it. That's why I added this information box here. So reading and writing geo packages with multiple layers. I already mentioned, was it week 2, that we started talking about vector data. The geo package is more than a shape file. It's not just a file. So you can have many layers, and you can store raster and vector data there. So when you're saving, you can specify a layer, and when you're also loading the data, you can specify a layer. So yeah, so there's a bit more information here in case you're curious, but we are using it here. So I'm saving it somewhere, but also I'm specifying a layer. And if you get a data set from somewhere and you're not sure, it's in geo package, but you're not sure what kind of layers are in there, of course, you can see it, for example, in QGIS. But if you wanted to use it from Python, Fiona, remember the library that allows you to read and write files, can also, it also allows you to list the layers that you have in your data. So Fiona.list layers, of course, you import Fiona, then list layers, you can get a list of the layers that might be in the geo package. Yeah, so doing overlay is fairly easy. We did just one example with intersection, but it is the same for other methods as well. So now let's move on to the next thing, which is data aggregation. So I will go to the next file, aggregating data. So we will continue working with the same data set that we just prepared. That's why we saved it. So we can load it here again. So data aggregation refers to the process where we combine data into groups. So you make it basically, you make the units bigger. So imagine you have a data set of population of different countries around the world. And what you're interested in is the population by continent. So from country, you have to move to continent. So you have to aggregate your data to a larger special unit of analysis. So that's what we mean by aggregating. So this aggregation can be based on a geographical characteristic, which is what we often do in GIS, but it can also be based on other columns in your data. So what we are actually doing here is that we are interested in one particular column in our travel time matrix. So it is car RT. So it's the time it takes to travel by car to Central Railway Station. So we are going to, as you can imagine, there are many grids around Helsinki. So imagine if you are interested in places that can reach, places from which you can reach Helsinki railway station in 20 minutes. Probably you end up with many grids around Helsinki. Now we want to aggregate them into one feature. So that's what we're going to try to do in this part of lesson. And of course, we'll start by importing the data. So let's use pathlib for defining the path. And here we are reading the file. So this is the same file you just produced, the intersection. So we are just focusing on Helsinki, not the whole Helsinki region. So for doing aggregation using GeoPandas, we use a method of geodata frames called dissolve that takes the input column. So it's a simple function. So let's do the aggregation and see how it works. So it returns another geodata frame to you. So I will store it with the name dissolved. So I'm applying the dissolve on my intersection data. And the parameter you need to provide is the column based on which you are doing the aggregation. So remember, even if you are doing an aggregation, back to the example of population per continent, if you want to do that kind of aggregation, you need to have a column in your data saying what continent each country belongs to. So otherwise, you cannot do the aggregation. So here we also are using that kind of column. So the column is car RT. So car underscore R underscore T. And once we do that, let's also get the head of the data to see what we get as the output. Okay, so the dissolve is done. So you have aggregated the data based on that particular column. So now that you look at the head, do you think anything unusual or different?
The car RT column is missing.
Yeah, exactly. So it is missing, but if you look at the left, you can see actually it has turned into your index. So when you do data aggregation using dissolve in GeoPandas, what happens is that the column that you have used for data aggregation becomes your index, as you can see there. So this can be good. For example, you can use ilog to quickly get all the rows that have, like, for example, here it's in minutes. So you can use the index to just get just quickly get the places where you have 20 minutes distance or travel time to center. But also it can pose challenges when it comes to visualization. But let's see, and we will see how to deal with this. So let's also run this cell, which basically calculates the number of rows you have in your data before and after the aggregation. So when we started our work, in the intersection data, we had 3,826 grid cells. And after aggregation, we have ended up with 51 rows in our data. So that's what we do by aggregation. So there were many places that had equal travel time to Helsinki railway station. That's why you ended up with less rows in your data. That's the whole idea of aggregation. Okay, so back to the thing with the columns. So let's investigate that a little bit more. So I want to look at the columns specifically. So in the dissolved data layer, I list the columns to see what I exactly have. And you were right, so there is one column missing. The column that you used for aggregation is missing. And as we already saw, it turned into your index. So it's not really missing, it just became your index. To confirm that, I will look at my index. So from dissolved, I access the index column. And you can see that your index is actually the car RT column, and you can guess from the values. So you have -1, these are the missing values. In the data, -1 is that they haven't been able to calculate the time. For example, if it's been an island or something like that. But the rest are the values in minutes. So probably 0 is somewhere right next to the railway station. Then you have places which are farther. Yeah, so your index is now basically the minutes. So if you want to just get, for example, places which are 15 minutes away from Helsinki railway station, you can just go with dissolved log, and 15. So can you guess what data format we have here? So if we are going to test it with type, but before doing that, can you guess what we have? So it's index 15. It's just one row of your data. So what would it be? It's a pandas series. Yeah. But to confirm that, let's try it with type. So I will try dissolved.log at 15 minutes. And yes, it is a pandas series. You're just looking at one row of your data. Okay, so now we want to make a visualization of our data. So specifically the areas that are 15 minutes away from the railway station by car. Yeah, so this is a series, so you cannot just visualize it like that. We need a geodata frame to do the visualization. So I'm going to make a new variable, and I will name it selection. And from GeoPandas library, I will access geodata frame for the conversion. So what is the data? You want to look at the dissolved log 15. So I retype that, dissolved.log 15. So this is what you want to put in your new data set. And of course, when you're creating a geodata frame, you have to specify what the coordinate system is. We haven't changed the coordinate system, so I'm going to just read the coordinate system from dissolved.crs. Because it's the same, we haven't changed anything. So let's run this. You see a mistake in my code.
Using like the parentheses before dissolve.
Here.
No, the other kind, like the way you have it in 15.
I don't see it somehow. Dissolve.log 15. Oh yeah, this one. Yeah, okay. Yeah, so now we made a selection of our geodata frame. Now it's easy to create the visualization. So I want to add the whole grid from Helsinki, like the dissolved one, and then highlight the ones that are 15 minutes away. So the easiest way to do that is to add both layers, just apply different color to the 15-minute one. So I will create my axis first using the dissolved.plot. And because this is not the highlight of my map, I will just add some neutral color to it. So I will go with a face color of gray. Next, I will add the same. I will add the selection, so the 15-minute selection, to my plot. So I'm adding it to the same map frame. And because I want to highlight it, I will add a color that has more contrast. So I will go with red, but you can try other colors. So this is a quick map of our data. So you can see the grids from which you can reach Helsinki Central Railway Station within 15 minutes by car. Okay. As I said many times, we will talk about making maps later on in a couple of weeks. But let's quickly create a map. And if you want to create a map of your data and just specify one column, for example, you want to apply graduated color. So you want to have a map like this, but apply a graduated color based on the time it takes to travel. For that, you need to specify a column. And the column that we need is the car RT. And now it's locked because it has become our index. So now what I want to do next is to release that column as index, so it becomes a normal column again. Then I will do the visualization and I will use that column for applying the color. So if you want to release your column, which has become index, there is a function called reset on index. So I will just overwrite my dissolved layer or variable. And I apply this method reset underscore index. So what this does, it releases your column from being an index, and it applies an automatic index for you. So from 0 on, so this usual geodata frame indexing. And also let's look at the head of our data to see what we end up with. Dissolve.reset index. Okay, so you can see that the column is back as a normal column. So you have the car RT again, and your index is the usual index that we have. So it doesn't have a name anymore, and it starts from 0. So it applies automatically an index to your data. So now that this column is free, then we can use it for visualization. And this is how you can quickly create a map, a thematic map of your data, specifying a certain column for the color. So I will go with dissolved again, and I will create a plot. And for my plot, this time I'm going to specify a column. And the column, of course, is going to be the column that we just worked on. So it was car underscore R underscore T. So this quickly creates you a graduated color map of the specified column. Okay, so that was it. But a bit of extra information, I put some information box about how aggregation actually works. So when using the solve method in GeoPandas, like we did just now, there are some default behaviors that we haven't touched in this part yet. So you might wonder how the aggregation works. So by default, it goes with firsts. You probably remember this from ArcGIS or QGIS. So when you do data aggregation, how do you aggregate? Which attribute do you keep in the output? So by default, it goes with first. But optionally, you can pass in a variable that we didn't. So we went with the default. You can pass in ag func. And you can provide a set of values. So how do you want to do the aggregation? First, it just picks up the first value. So it's a bit like random. But if you want to get the sum, or if you want to get the mean or the maximum, the first, the last, you can specify. So you can go with aggfunc and provide a value here. If you don't, it just by default goes with first. And the geometry aggregation. So we already talked about what happens with the attributes. When you do aggregation, they're unioned. So essentially, so the grids that we had were just unioned into the same. That's why we ended up with less rows in our data. So we had many grids that had the same value, 15 minutes, for example. So what happens is a union of the values. Yeah, so there's some details involved, and of course you can read more from the documentation if you want to be sure how it works. If there are no questions, then we can move on to the next part, which is rather short. And that's simplifying geometries. So like I said, simplifying geometry is more of a cartographic thing. So if you're producing a map, depending on what's the purpose of the map, sometimes you don't want so much detail. So for example, if you're making a big map of the country that is not going to be used for navigation, then it doesn't matter if you have all random curves of a river included. You just want to show the overall whereabouts of the river without having too much detail. So very often we do simplification for cartographic purposes. So now we are going to work with the Amazon River in South America, and it has a complex shape. So we are going to simplify it a bit and create a simple version of it for example, for adding to a map. So let's start by defining the path to our data. And the next thing we are doing, of course, is reading the file. We have a shape file. Well, it's a geopackage of the Amazon River somewhere in our data directory. Let's just load it and look at the head of the data. So it's just one river. We have only one row of data. So the data is not big. We have a multi-string of the river. So let's look at the CRS of our data. So amazon.crs. Yeah, so you have a Mercator 2SP. Probably unfamiliar to many of us because we don't use it in this part of the world much. So, but what matters to me is the unit of the distances, because you have a simplification, you are working with units, so it's in meter. So that's what matters most to me here. Let's also plot our data quickly to see the shape of the river. So amazon.plot. And so this is the shape of our river, and you can see we have a lot of details and we want to simplify it a bit. Yeah, so here is a link with more information about the projection system used, but as I said, what matters to us right now is that it's in meters, because the parameter we provide for simplification is based on the unit. So simplification is very simple, and it's provided to you by Shapely. So it's a Shapely feature that you can access via GeoPandas. Yeah, so what you do when you simplify, you essentially create a new geometry in your data. Remember, when you have a geodata frame, you already have a column named geometry, which we looked at up here. So we are going to create a new column, a new geometry that is just simpler. So let's do that. So that's why I'm going to give it a name, because we already have a geometry column. I'm going to name the new one simple geom. And this is how you do the simplification. So Amazon.simplify. And you provide a tolerance. And this tolerance is in the same unit as your data. So that's why we checked if it is in meters. And very often with this, you just do trial and error. You go with different tolerances to see what level of simplification is enough for you. So as tolerance, I go with 20,000 meters or 20 kilometers, which makes sense here because we have a very long feature. And I've tested this before. 20,000 looks good. So I will skip one step here. And let's just run add this Amazon.plot. So let's see what we get as the output. Do you see any difference? Between this plot and the one we applied earlier? We created. No? So why don't you see the difference already? We kind of talked about it. So now try the head of your data, see what you see there. So when you applied the simplification, you essentially created a new geometry column, but you didn't tell GeoPandas to map your data using that geometry. So that's why we skipped this step to produce this. So now we have to set the geometry. So I'm going to tell GeoPandas that, okay, I have more than one geometry column, so don't just by default go with the one that is named geometry. I want GeoPandas to use this column instead. So using a function called setGeometry. And here you can specify the name of the column. So we created a new simple geometry and we named it simple geom. Okay, now if you run this, you will end up with the more simple version. So if you compare the two river outlines, you will see that this one is much simpler. And you can try, if instead of 20 kilometers you go with 40 kilometers, you will end up with a more simple shape. Okay, so remember, this is done by Shapely, so it works with geometry, and what it does, it adds a new column. So if you want to see the changes, then you have to tell GeoPandas that use this geometry instead. Otherwise, it always goes with the default, which is the column named geometry. In this case, it was simple geom, so it wasn't the default value. Yeah, so simplifying features in GeoPandas is simple. So let's move on to the next part, which is a bit bigger part of the lesson today. And that is reclassification. So reclassification is something that we have done many times. Most often you encounter reclassification when, well, in many situations, but very often it's for producing a map. And we all have studied GIS, we have all studied cartography, and you know that the map you produce is heavily affected by the kind of classification you use. You know, there is a classic book, How to Lie with Maps. And one of the best ways to lie with a map is to just mess with the classification. You're not necessarily lying, but you can just bias what people think based on the classification you're using. So classification is very topical in GIS, and we are going to use classification. We will see how to work with it, and there are a few ways. So first of all, we go with some of the built-in classifications. So you're all familiar with the natural breaks, the Jenks method. That is the default value in ArcGIS, the default classification usually, unless you change it. So we will see how we can apply natural breaks or quantiles, different methods, but also we will see how we can create our own custom classification approach. Yeah, so first we will start with the common methods of classification, and then we use our own custom classification, which is basically to answer a certain question. So we are going to continue working with the travel time matrix, and we want to find a home. So our home, we don't want our home to be too far from center, railway station, so we have a condition that it should be less than 30 minutes away. But at the same time, we have a budget constraint. So you don't, normally if you are very close to center, the rent is very high. But your budget is limited to 1,000 euros per month. So using this criteria, having 30 minutes access to central railway station, still having a rent less than 1,000. We are going to use this as a custom classification later on. So all the classification that we do in GeoPandas is provided by a library called Map Classify. So it's a very powerful library, and it allows you to do many things. So it's part of a bigger library called PySal, which we don't cover in this course, but it is a good library for doing a special statistics and a special analytics. So Map Classify is part of that library, and it allows you to handle classification. So it is built in GeoPandas. Unless you want to make your own custom classification, we don't need to explicitly import Map Classify. Yeah, so that was the introduction. Let's get started and do the work. So again, we import the data, we define the path, we import the data. So the data is the same. We are working with Helsinki travel times to railway station. And we are printing the head to just remember what kind of data we are dealing with. Yeah, so same data set. We don't need to spend too much time on it. So classifiers. There are a lot of classification methods, and there's a link to the PySal library, to Map Classify module. So you can read more about these methods, and many of them are well known, so there's a lot of information out there. For example, you can use box plots, you can use equal intervals, there's Jenks method, Fisher-Jenks, natural breaks, quantiles, percentiles. So there are many methods to choose from, and these are built in. So if you need any of these for your work, you don't need to write your own code. Map Classify allows you to do that, which is very nice. And most often you find something from here that is enough for you. But we will also see how you can make your own classification. So now we are working with a different column in our data. So it's PTRTT, so it's public transport travel time. So before we were working with the driving time, now we want to look at the public transport time. And as we already noticed in our data, the no data values are represented as -1. We already saw this in the first part. So one important thing to do here, last time in the part we did earlier with the data overlay and everything, we didn't remove the outlier or the missing data because we just wanted to produce a visualization. And we kind of saw it as black dots in our map, or black grids. Here you want to do classification. And in classification, you're working with values. So if you have a value of -1, it's just going to mess up with your classification. That's why it's important to remove it. Otherwise, it just skews the data. So you suddenly have a minus value. So that's what we are doing in the first step. Simple. We're just applying a condition. So we only keep values that are bigger than 0 because we know -1 is the missing value. So let's just run this. And we end up with a clean data. without any missing values. Okay, so there are a few situations. So if you're using the classification only for visualization, then it's very easy. There is a parameter you can pass into your plot and say which classification you want to use. So if you want to just use classification for data visualization, you don't need to do much. And this is the first thing you're going to do. But if you want it in your data, if you, for example, want to add the classification as a column in your data, then there are a few extra steps to take. But as a first thing, let's just use classification for our visualization. So I want to visualize this data that we just cleaned. So I will just copy and paste the name of it. And then I'm going to create a plot. So we already saw this. We want to create the visualization based on a particular column. And the column is the public transport travel times. So in GeoPandas or Matplotlib, actually, if you want to specify the classification method, there's a parameter called the scheme. So the scheme tells, through this variable, you tell Python which classification to use. So I'm going to go with natural breaks, and this is how it is written. So you have to check the documentation and see the exact spelling. So it's natural breaks with the underscore in between. So from the documentation, you can see how to type this. So natural breaks is typed like this. So as you know, with natural breaks, you have to specify how many classes you want. So you provide a value for the parameter k. And I've tried this before. With 9 classes, the visualization looked decent. So I will go with 9 classes. As you know, with classification, you have to have a good idea how to do this. And usually it's by knowing the data and doing a bit of trial and error. The next thing I'm going to do is to apply a color. I don't want to go with the default color. So I will add a color map. And we are going to look at this later when we talk about visualization. And from Matplotlib, there are a bunch of built-in color maps you can use. I will go with one that ranges from red to blue through yellow. So it's spelled like this. So RD, yellow, YL to blue, something like that. So this you can get from the classification. So there are different values. You can go with reds or browns. That is a shade of reds. So there are many built-in colors to choose from. Then line width, because we are working with a grid, and if you include the lines, it's going to get very messy looking. So I'm going to set this to 0. So I don't want to apply any outline to my grids, because otherwise, you end up with all those lines. And do you want to add a legend? If yes, you can set it to true. Okay, so you can see it already takes a bit longer than what we have usually had. And the reason is that you're doing classification. So you have a large data set, a few thousands of grids, and you're reclassifying them. So it might take a few seconds. But still, it was fairly fast, and you end up with a nicer looking map than what we had before. So you have done a classification, and the color map you chose was ranging from red to blue. So you can see the smaller distances are red, and the farther the places, it's yellow and then blue. So this was based on public transport. Let's create the same map, but this time using a different column. So I'm going to just copy this whole line and only update the name of the column. So instead of the public transport time, I'm going to visualize the walking distance, and it is called walk_d in the data. Everything else is the same. So I'm going with natural breaks. I'm asking for 9 classes, applying the same color map, and all is the same. And this is what you end up with. As you can see, with distance, it's of course more radial, the pattern, because it's distance. The farther you are from the place, the bigger the distance is. But with, of course, public transport, it's a bit more complex because of accessibility. So you kind of see the same radial pattern here, but for example, along the highways, the travel time is shorter. But this is distance, so you end up with this radial pattern. Okay, so this was classification if you are just using it for visualization. You just provide a value for a scheme. Now we just work with natural breaks, but this could have been quantized, it could have been Jenks method, it can be anything. Now we want to use the map classify library, which we already were using without explicitly naming it. But now we want to do it so we can apply the classification to our data, not just for visualization. So I will import the library called map classify. So I'm going to do the same thing this time, but directly from map classify. So from the library map classify, I will access natural breaks. So there's a function defined natural breaks that applies natural breaks classification for you. So you have to provide a column. So on which column are you applying the classification? And the parameter for that is y. And here you have to give the name of the column from your data. So accessibility grid is the name of your layer. And now we are going to work with the public transport time. So it was called PTR_TT. So this is the column that you're using. And of course, you have to specify how many classes you want to have. So k equals 9. So now using the library directly, you're not applying it, you're calculating a classification. So this is nowhere in your data yet. So it just tells you that this is the value. The values you get may not be exactly the same because natural breaks has also a bit of randomization in it, but roughly it should be the same. Yeah, so these are the classes you end up in, and it gives you a count of how many of your rows of your data have fallen into that class. So let's try another classification method. So I will just copy what I have here and make some modifications. So now I want to go with quantiles, which by default gives you 5 classes. So you don't have to provide the k anymore because you're going with the default 5 classes. We will use the same column, so we don't need to change anything there. But of course, we are changing the method of classification. So instead of natural breaks, I want to use the quantiles. And now you end up with 5 classes with roughly the same amount of points in each class. So sometimes it's useful to be able to extract the threshold values. So now you know these are the thresholds. So this is where the class is defined. So the first break is at 41, 52, 66, 85, 199. So how do we extract those values? You can get the bins from your classifier. And we are, for example, going to use this later to make a visualization at the end. But this time, let's do the same thing, but we store the output in a variable. So last time, we didn't store it anywhere. So you don't have to type everything. I will just copy from up here. So I'm repeating this part, doing the natural breaks. The only difference is that I'm storing the output in a variable called classifier. So in order to access those thresholds from the classifier that you just created, you can access the bins. So those are called bins. So these are the bins. So you extracted those values that you had up here. So 32, 44, 55, 66, 77, and so on. So we will see a use case of this, but now we know how to access it. Yeah, so far we have been calculating the classification, but we haven't applied it to our data. Yeah, so when you create a classification, and here you have it stored in a variable, you end up with a classifier object, which is essentially a function that would do the mapping. It's a function, which means that you can apply it to your pandas data frame using apply, which we have seen before. And that's what we are going to do now. Okay, so I'm going to create my classifier. So with map classify, I will create natural breaks again. Okay, map classify natural breaks to page. Okay. So I'm adding one thing here, make, to create the function, and I will show you the output. And k equals 9, so I will go with the same. So once you do actually make, then you actually produce the function that you can apply. So there's one step to take. So classifier, map classify natural breaks, and this turns it into a function, which you can then apply to whatever column you have in your data. It will just apply the natural breaks or other classifications. Okay, now that we have our function, we can apply it. So I will create a new data name, data layer variable. So I will call it classifications. And I'm going to apply, for me it's very hard to type this, accessibility grid. So I'm going to apply this on my data. So remember, we specify a column. So on PT, RTT, which is the name of the column I'm interested in, or I'm going to apply the function that I just created, which was this classifier option function. So remember, you create using make, you create the function, and then you can apply the function using the pandas. And let's also add the head here to see what we get as the output. Okay, so you did the classification, you end up with some classes, and you see the classes here. This is the head, so you're seeing the first 5 rows. So you applied a classifier, Jenks natural breaks classification on this particular column. So now let's check the type of data we have as the output. So if I just check type of classification, you can see that we ended up with a data frame. So we have a table like this. So what this did is that it just created a new data frame with the classified values. But if you want to just add the classification as a new column in your own data, then that is also easy, and we have done similar things before. So you just define a new column here. So in my accessibility grid data, I'm creating a new column called NBPTR. So it's the same name, just added natural breaks at the beginning. So I know that I'm storing the natural breaks classes here. And the rest is the same. The only difference is that you're just storing it in a new column. And then we are printing the head of this new and old column to see the output. Yeah, so these are the old values. So public transport time was 133 minutes, and now it's in class 8. Now that we did our classification, we can visualize. So let's go with our visualization. Accessibility grid.plot. Specify the column that you want to visualize. Remember that we want to visualize our classified data. So we had named it MBPTRTT. So this is the classified column. Again, I want to hide the grid lines. So I will set the width to 0. And I would like to have the legend added to my map. So a quick map of our data using the classified value. So if the purpose of your map, if the purpose of classification is to produce the map, you didn't have to take these steps. You could have just used scheme. But of course, you can do the classification manually, add it to your data, and then use that column to produce the map. When working with classification, one useful thing is to draw or plot the histogram of your data. It gives you an understanding of the data distribution. So that's often a good starting point for visualization. And this is something that, well, we have created plots already in the first part of the course. So we know it's easy. So you can create an accessibility, you can create a histogram on your accessibility grid data. So I will apply it on this public transport time. So PTR travel time. So dot plot. But here I say I want a histogram. So you put hist, short for histogram. With histogram, you should specify how many bins you want to have. So I want to have 50 bins in my data because I have such wide range of values. So 50 has worked well. So let's run this. And you end up with a histogram of your data value. So you see there is a peak around 50 minutes of travel time. So a lot of areas have around 50-minute travel time to Helsinki center. So remember, we already learned a way to get the bins. You remember the bins, the thresholds of the classification. So here we are, the code is typed in, so we just run it, but let's see what we have. So we are creating natural breaks classification. We are creating the histogram, but we are adding lines of bins. So let's run this and see what we have, then it makes more sense. So we created the same histogram, but we added these vertical lines of the bins. And you can use that, you can use PLT X V line, which is X vertical line, to add lines. And we are getting the values of the lines from the bins of the classification. So this gives you an understanding of how the classification is working. If you end up using natural breaks, these are where the lines are drawn or where the bins are defined. So as I said, classification is very important and can significantly affect your results. So it's good to explore different options. So exact same thing, but if you use quantiles instead of natural breaks, you will end up with this kind of distribution. So here there is a practice. I will skip it, and we might come back to it if we have time at the end. But basically practicing to apply the same thing on a different column. But let's skip it for now, and if we have time, we come back to this. Yeah, so applying a custom classifier. Remember, one of the so we wanted to look. So the question here is that we want to buy a home or rent a home, and we don't want the home. We want it to be fairly accessible, so we have reasonable travel time to center. Let's say less than 20 minutes. But we also want the home to be rather cheap, or less than 1,000 euros. Depends on your definition of cheap. But in this data, we don't have rent. And we don't want to complicate things. So let's just assume that if you're super close to center, the rent is very high. So I'm using the distance here as a proxy of the rent. So I want to look for places which are within 20 minutes travel time from Helsinki center, but they are more than 4 kilometers away. So they're not right next to railway station. So I'm assuming that if it is 4 kilometers away, then probably the price is within my budget. Just as a proxy for rent, because we don't have rent data. So that's what we want to do. So this is a specific classification. It's our own classification. We don't want natural breaks or anything. This is what we are going to use. So this is just an example of how you can do the classification yourself. You might have other criteria for different situations. So to check, well, this is basically this translated into Python. So we have distances of travel times of less than 20 minutes with public transport, and a walking distance of more than 4 kilometers. And we are applying it just on one of the rows, the first row in our data, to just see what we get. So it returns a Boolean value. So using this condition, of course, you can apply the same condition to your data. So let's copy this whole thing and try it on another row of our data. So the first one was false. So the first row in our data doesn't meet the criteria. But I've done my research before, and I know this row probably has a true value. So 11,293. And it's true. So I don't remember where that is, but that cell meets my criteria. It's somewhere within 20 minutes travel time and more than 4 kilometers walking distance away. So if you want to apply this So this is very similar to what we have done previously in pandas. So you have a condition, and based on this condition, you can create a new column. We call the new column suitable area. So it's either 0 or 1. So the place is either suitable for us according to our criteria, or it's not. So I'm just applying this function using lambda. And many of you have used lambda before in the exercises, so you probably know how it works. So I'm applying a function here with the same condition that we typed in up here. So we end up with a column that has Boolean values. Each grid cell either meets my criteria or not. So in order to make sure you are understanding this, let's take a few minutes and do the exact same thing without lambda. Just define a function and apply it there. So you get it to make sure you understand what is happening here. So define a function, whatever you want to name it, and instead of lambda, just apply that function and do the classification. Okay, so I already typed in the answer here, but without this, did any of you manage to get the output? Or did you have proper progress with it? So Lambda is a bit confusing, at least for new learners. I'm personally not a big fan of it, but it's common, especially in the world of pandas. So what Lambda does is the structure is like this. So Lambda arguments is the input of your function. So in this case, you're applying it to the row, and then the expression. So that's how Lambda works. And I guess you have used it in your exercises already. At least it was an option. Yeah, so it's an unnamed, simple, easy function. It works well, but it's if you just have something like this as you only use once and you want to keep your code short. But if you want a function that is reusable, of course, this is unnamed, so you have to type it in every time. So for example, in the first period, we had many examples of temperatures, like Fahrenheit to Celsius or vice versa. If you want to reuse that and you write it like this, you have to copy and paste that piece of code every time. So I'm personally a fan of going this way, but that is shorter, more elegant solution. So I define a function called isSuitable, and I apply the same condition, and it returns a Boolean value, 0 or 1. So this is Boolean, true or false. When I convert it to integer, it becomes 0 or 1. And then I just apply it like a normal function to my pandas. And remember, axis 1 means that it just goes vertically and applies it to all my rows in the data. So both of these would give you probably the same from the same output. And now we have ended up with a new column called suitable area. So before we move on, let's print the head of the data. So accessibility grid dot head. Accessibility. Do I have a typo again? Yeah, so you ended up with a new column called suitable area with Boolean values, so 0 or 1. Well, the first 5 ones are all false. Probably there are not many places like that are very accessible but not too far. But yeah, that's basically what we did. We did the classification manually. The same thing that Map Classify did for us automatically, we did it manually. So now we want to see how many potential areas exist meeting our criteria. So with accessibility grid, I look at the column that I just calculated. It was named suitable area. And I want to do a value count. So value underscore counts. So I have 13,000 places or grid cells that do not meet my criteria, but there are 9 places, 9 grid cells that meet my criteria. So I might actually get lucky and find an area that is accessible and not too far from center. So now I'm curious to see where those places are, and that's why we are creating a plot. So yeah, so we are just mapping the suitable areas. Let's run that. And here you see you have some. Yeah, so you have some areas in the east that meet the criteria. Yeah, so where is this actually? Is it like Herttoniemi or where is this? Yeah, yeah, so somewhere there. You have some places that are probably around the metro line that you can reach center fairly quickly, but they're not super far, but they're far enough from center. Yeah, and that was it for today. we will work with the similar things in the exercise. And you have the auto grading. Hopefully it behaves well. And see you next week.